Ron Selly, and I'm the program director for HAS, and it's my pleasure to introduce Larry Mitchell. But if you don't mind, Larry, before I start your introduction, I got a couple of real quick things to say. I'm really excited to be here because for our first face-to-face meeting in a long time. And I actually drove 3.5 hours to get here. I live out in the hill country nowadays. All right, so, but that being said, I think it's also a tremendous coincidence that we had a really good update from Joe Caleb about Texas Star Party. I really want to kind of emphasize what Joe was saying. I think there's a lot of excitement now about the fact that TSP is kind of trying to get back to what it was like when I first went in 2003. Okay, and that's my segue into introducing Larry Mitchell. I don't remember for sure whether I met Larry in 2003 at the Texas Star Party, but I know I did it the next year, 2005, because I kept hearing all these people telling me about this visual observing list from hell. Okay, and Larry was the author of that observing list. If you've been around HAS for any length of time or attended TSP, especially if you're a visual observer, I don't have to tell you much about that, about Larry. And if you have a second phone back, those of you who don't know Larry, Larry's been an astronomy, involved in astronomy since he was a young boy of 10 years old. He's the author of a book series called Visual Mysteries of the Universe. And there are the 3 volumes of it up here. And since 2000, Larry has been the chairperson of the Advanced Visual Observing Program at Texas Star Party. He's also been awarded the TSP awards of Lone Stargazer and also the Omega Centauri Award for outreach. And Larry's other astronomy accomplishments also include the discovery of a supernova, SN 1994S, which was a type 1A. And in his early days, and I think this is why Larry got into the observing list from hell, he cataloged over 117,000 galaxies for the called the Mitchell's Anonymous Catalog, and it's found in the program Megastar. And our belief, again, one of the things I know Larry from is that he's the only person I know that has actually observed William Herschel's full observing list. Okay, so we're talking about a guy who's really accomplished an awful lot in visual observing. So much so that Larry has been like an asteroid. Asteroid 126183, Larry Mitchell was named in his honor. So with that, I'll turn the program over to Larry.
Thank you. All right, welcome everybody. This is fantastic. The people that put this together where we can have meetings and see what people look like and visit with each other like we did 5 years ago. This is wonderful. This is absolutely wonderful. Stephen, Matt, whoever else was involved in this, let's give these guys a big hand because this is terrific. It works. Okay. A couple of things. We as amateur astronomers or semi-professional astronomers, we're very fortunate. We have at our ready, willing, and able hands the Hubble Space Telescope information, the James Webb Space Telescope information, the Gaia spacecraft information, the Chandler X-ray spacecraft information. We can pull this information up anytime we want it, and it's easily accessed. People like Edmund Hubble, Barnard, Alan Sandage, those folks would have killed for what we're able to do on a daily basis. What I'm going to do here is walk you guys through a little bit of the Stellafane Star Party, but also I'm going to try to cover the entire universe, which is a challenge, but I'm going to do my best. But first off, okay. First off, I want to say something about my friend Al Nagler. And we were friends, I'm very proud to say. I've known Al since, my goodness, 30 years ago back at the Texas Star Party, when he used to come down and look through my telescope, my 36-inch telescope, and then he'd try to sell me an eyepiece, which is the way Al, which was his basic nature. Hold on, sir. I should be able to see the next screen on this. You know what I'm talking about?
Present.
There, yeah, it was on there a minute ago. Okay, thank you. Technical difficulty. Okay, but Al was a very friendly, very open, very giving person. He headed up Teleview Optics Company since 1977. He was the man that got that started. But he was very easy to get along with and a very, very nice person. He started out back in the 1950s. Like in 1956, he went to work for an optical company. And from there, he worked his way up to chief engineer for the optical company. And then shortly thereafter, he started designing optics for NASA for the lunar lander program for the Gemini and the Apollo astronauts. In 1960, he married his wife to be Judy Perlman. And she was just like Al. She was very outgoing, very, very talkative, and just a wonderful person to be around. And Al told me on their very first date, they went out for dinner, and they brought them, the servers brought them a piece of cake, which they ate. And after that, they brought them a second piece of cake. And Al said, well, we didn't really order that, but anyway, here it is. He said, Judy, and this was his very first date with her, said Judy got out of her purse a piece of paper, and she wrote something on it real quick, and then got a knife and put a little slit in the piece of paper and inserted that paper into the loaf of bread and then sealed it up so you couldn't see it. And Al asked her, says, well, what did you write? And she said, I wrote on the paper, whoever gets this used piece of bread, I hope you enjoy it. And Al said he knew right then that was the girl for him. They got married in 1960, and she was with him at work last week when he died. So they were together the entire time. Teleview was a family-run operation. Judy was the manager. She ran the office. His son David was in charge of manufacturing and testing. Merrill, his daughter, she filled in whenever she could. And they were a very tight-knit family. Okay, that I can't really point to that, but the one on the left, that was taken just this last July. This may be one of the last pictures taken of Al that we had at breakfast with them. And the picture in the middle was taken last year at Stellafane, and that is Judy with Al. And then on the right is a picture taken with Al 2 or 3 years ago at our observing site. But Al, his first Stellafane was in 1958. He won third prize for the best telescope design. And he told me he had been to every Stellafane since then except one in 2020. He missed when Stellafane wasn't in operation. So he was a fixture. And every year he gave away between $8,000 and $10,000 worth of eyepieces to Stellafane. He had a physics degree in 1969 from the City College of New York. And as I say, he went to work and founded Teleview in 1977. And the first telescope eyepiece that he manufactured sold for $200 when the average telescope eyepiece was selling for $50. And he was afraid they were going out of business and he couldn't sell them fast enough. And to this day, my eyepiece box is full of nothing but Teleview eyepieces. The last time I saw Al, he was trying to sell me a Type 7 Nagler eyepiece, which is typical Al Nagler. He will be missed, but certainly not forgotten. Okay, a little bit about Stellafane. On the left is what we call the Pink House. This is a picture in the middle is the Pink House and the Porter Turret Telescope. Stellafane started in 1920, where Russell Porter got together with 15 men and one lady who was a school teacher, and she taught them how to grind mirrors and build telescopes. And they did that until 1923. They formed the Springfield Telescope Makers Conference, which is their club. And at the same time, they built this clubhouse, which is covered in pink paint. And the reason for that was the local paint company only had pink paint enough to paint something of this size. So it's been the Pink House ever since. And interestingly enough, the name Stellafane came from Stellaphanum. Stellaphanum was Russell Porter's name for the Pink House. Stellaphanum is Latin for shrine to the stars. So the name for the Pink House became the name for the founding star party, Stellafane. In 1926, they had the first star party. They invited the townspeople from Springfield out, and from there on, we had star parties every year, except they missed a couple of years, World War II, and then missed 2020 because of COVID. Everybody that is interested in amateur astronomy should go to Stellafane at least one time, just to see the history. The picture in the middle is just like it was back in 1926 and in 1930. That turret telescope was built. It's actually the second type telescope like that, but you can sit inside the building with a heater and operate the telescope. So if it's minus 20 degrees outside in Vermont, you're in a comfortable environment looking at the night sky. Russell Porter invented that technique. The light, I don't know if I can point to it, the light hits the secondary mirror, which is here. It bounces off this 9-inch primary mirror out here and then back through a hole here into inside. Basically is the way that works. But it works very nicely, and let me see. All right, this is some of the telescopes that they built. This is in the basement of the Harkness house. And those telescopes look just like the telescopes that we build today. The mirrors are still in them, and all of those telescopes were built in the 20s. The one in the middle is a stand-on-the-ground telescope because the counterbalance is up front, so you can stand on the ground and look through the telescope, and it stays balanced, which is pretty slick. This is my partner, Eileen Myers. We do the observing program for Stellafane. We've been doing it for the last 9 years. And she is a core member of the group and a thorough joy to work with. She and I, she designs the pins, and I do the observing programs, and we work very closely together. This is the observing field. We call our program the Observing Olympics. And this is on the left here is the Observing Olympics chair, tables and everything. That's our 13-inch telescope. And this is the main observing field. They say before we started doing this that there was 2 or 3 telescopes out there at any given time. With the Observing Olympics, by the time, this is early in the afternoon, by the time it was finished, that field was full of telescopes. And it's kind of amazing because Stellafane has between 1,000 and 1,600 people that show up every year. Most of them do not do astronomy, but the people on this field are as avid observers as the people at the Texas Star Party. They're staying up all night to get an observing pin that we hand out. This is the clubhouse. That's me giving a talk. On Saturday nights, we have meetings on the Hill, which is what they've had since 1926. And it goes very nicely. If it's raining, that we're back inside the building. And the night skies are very good, surprisingly so for Vermont. That's a very populated area. But if the night is clear, it's usually a very, very decent skies to observe with, surprisingly so. This is the observing list. This is the one that I made up this year. And the title was A Little Bit of Everything. And I covered quasars, galaxies, globular clusters, open clusters, planetary nebula, emission nebula, and dark nebula. Pretty much everything. I started out with a lot of these objects, these items, with this talk, but I have modified it a little. So this is not the same talk that I gave at Stellafane. These are the pins that we've handed out over the years. And as I say, these people up there are as avid observers as the Texas Star Party people. I catch just as much grief from them about the observing list as I do at TSP. And it's all good-natured and it's all a lot of fun. But it's a fine bunch of people up there, and I would recommend everybody to go to Stellafane. If not for the observing, just for the historical aspects, because everything we do, our observational astronomy, it started there. 1926 is when they had the first star party anywhere in the world, and from there it's mushroomed into what it is today. So it's worth seeing, if nothing more than just that. All right, a little bit about the universe. Quasars. To understand quasars, you must have an understanding of cosmology. And cosmology is something that a lot of astronomers, amateur astronomers, try to stay away from. I find it a fascinating subject because it's not guesswork, which a lot of people think it is. These quasars are not millions of light years away. They are billions of light years away. And that's a huge, huge jump in time, because to go from 1 million seconds of time takes 11 days. To go to 1 billion seconds of time is over 33 years. These quasars are not 1 or 2 billion light years out. Some of them are 15 or 20 billion light years out. And that's kind of controversial amongst a lot of people, because we know it's a pretty much fact that we live in a universe 13.8 billion years old. A lot of people say, well, nothing can be further away than 13.8 billion years. You know, that's the standard way of thinking with most people, and unfortunately is 100% wrong. And I'll try to convince you of that, oh ye non-believers. Okay, redshift. When we say redshift, it's symbolized by the small letter Z. But that is a time function. Once we get beyond 2 billion light years out, because within 2 billion light years, gravity takes over and the expansion of the universe is not totally in effect. But when we get to cosmological distances, redshift is not a distance, it's a time factor. It's how long that light took to get to your telescope. In 1920, the entire universe was available before Hubble discovered the expansion and stuff. When astronomers went out and looked at the night sky, they envisioned they were looking at the entire universe. They had no idea how big the universe was. So the Milky Way galaxy was the entire universe. And that was only 100 years ago. Just think how far we've come, since then. Edwin Hubble, and of course he had a lot of help. Hubble gets a lot of credit, and he was brilliant. He was a Rhodes Scholar, and he did a lot of really wonderful things. But he couldn't have done it without Milton Humason. He couldn't have done it without Vesto Slipher. He could not have done it without Henrietta Leavitt. These people did the redshift figures that Hubble used. Leavitt did the Cepheid variable information that Hubble used. So not to take away from Hubble, but he had a lot of excellent help in what he was doing. In 1924, he discovered a Cepheid variable in M31. And that told him that the M31, the Andromeda Galaxy, which we call it, he called it a white nebula, that it was actually outside of our Milky Way galaxy. That's the first time anybody knew that there was something beyond the Milky Way. That was 1924. In 1925, with looking at spectra and looking at Doppler redshifts, he determined the universe is expanding. So between 24 and 29, the universe just mushroomed. Our knowledge of the universe just went crazy. And things kind of puttered along until 1997, 1998, they discovered that this expansion of the universe, which had been expanding in a linear fashion, of about 70 kilometers per second per megaparsec, all of a sudden, for some reason, started speeding up. And even worse, it started speeding up not in the same areas, but in different places. Over here, it was 4 billion light years. Over here, it may be 6 billion light years. And they don't know why that speed up was undertaken, but we call that dark energy. And we still to this day don't know why it's speeding up. But the people at McDonald Observatory with the Hobby Eberly telescope, with the 10-meter Hobby Eberly telescope, are leading the charge on this, trying to figure out what dark energy is. It's more obscure than dark matter. We don't know what dark matter is either, but it has something to do with gravity. But they have no idea what is causing the universe to suddenly speed up. So right now, we live in a universe where we figure 70% of it is dark energy, 25% of it is dark matter, and we can therefore account for only about 5% of the known universe. So it's somewhat embarrassing. But all of this goes back to the redshift theory. But you figure from 1926 to now, the leap that we've done in observational astronomy and just astronomy in general, where were we going to be 100 years from now? And hopefully we will be a little bit better than that. It's 5% of the universe we can account for. 100 years from now, people may be laughing at us. They may be looking at us like we looked at Edwin Hubble and his people back 100 years ago. Who knows? Distance scales. There's various ways of measuring distance. On the left is a standard tube for objects that are close by, where you measure the Doppler redshift of absorption lines in a spectrum. If they're shifted to the right, they're red shifted. They're receding away from us. If they're blue shifted, they're coming towards us. And the amount of that shift will give an idea of how far away the object is and whether it's moving this way or that way or whatever. The trigonometric parallax uses the base of the Earth's orbit in a 6-month base to measure how much shift background stars do. And you can see that if you look, put your fist out, open one eye, open the other eye, and you see the shift in your hand. That's parallax that we're measuring. And if you go out far enough where a star in the background will shift 1 arc seconds, that's 3.26 light years. And that is a parsec, which astronomers use as a standard method of measuring distance. And parsec is short for parallax seconds. So parsec, parallax seconds. So that's how they came up with the name. But that's for very close-in objects. For cosmological distances, if we use luminosity distance, if we say, okay, something is so far because of its intrinsic brightness, well, that throws things off because galaxies, if they're receding from us, they appear further away than they should be. They're fainter. So that luminosity distance gives an incorrect measurement, although a lot of people use that. If we use angular diameter, well, that throws things off in the opposite direction because we took that measurement before it moved, so it appears to be larger. Galaxies were much closer when that image was taken, so they appears to be larger and brighter. So that's not really good. What people are using now is something called proper distance, co-moving radial distance. And this works only for the current epoch today, but it expands with the universe, and it's where galaxies are right now, and it takes into consideration the effects of dark energy, which is what I mentioned a minute ago about the expansion of the universe. This is the most accurate way of measuring how far objects are, but it also leads to some controversy as to how far these objects are with some people. Again, the redshift is a light travel time. When we're looking at cosmological differences, it's a light travel time and not a distance factor. So history of the universe, we got the Big Bang 13.8 billion years ago. We had sudden inflation, which lasted like a few nanoseconds, and then inflation. We get to a region called nucleosynthesis, where protons and neutrons mated together, but electrons were still flying around. It was too hot to form true atoms. Those electrons reflected light, and we had a state of what they call plasma, and we cannot see that. We cannot see into or through plasma. After about 380,000 years, the electrons, the temperature of the universe calmed down so that electrons could attach, and all of a sudden the universe became transparent, and that is the earliest light that we can see. When we look at the radio background, we can actually see that light, that 380,000 year light after the Big Bang. And since then, the universe has been expanding. After a few hundred million years, a galaxy is formed, and 4 to 6 billion years ago, we have dark energy, which is causing the universe to expand at an increasing rate, a big increasing rate. But all of this is not guesswork. They're pretty sure that this is the way things happen. So how do we know the universe really is 13.8 billion years old? If we combine the cosmic microwave background, which is at 380,000 year old after the Big Bang light that we're able to see with radio telescopes, which is the faint afterglow after the Big Bang, if we combine that with the expansion of the universe, which we call Hubble's law or Hubble's constant, which is anything but constant, but it's typically somewhere around 70 kilometers per second per megaparsec, or for those that are metrically challenged, 43.5 miles per second. What that really means is every 3.26 million light years, the universe speeds up by 70 kilometers per second. 70 kilometers per second every 3.26 million light years. That's a tremendous number. And it's been going on and on and on and on until dark energy takes over and it gets even faster. So the edge of the universe is much, much further out than anybody imagined. But if we take that expansion of the universe, Hubble's law, and if we take the cosmic microwave background and we reverse that, if we go back in time, voila, we come up with a few million years of 13.8 billion years. So that's how we know that that is the age of the universe which we live in. It's all complementary information, and it's scary how close that calculates out to be. So, along with the controversy of how big the universe is, these are some heavy-hitting names that I've put up there, and all of these people, in some form, fashion, or another, had something to do with this expansion of the universe. During the universe's 13.8 billion year existence, when light from distant objects approached Earth, they came this way, the universe was expanding. The whole time that light was coming this way, it was expanding. But at the same time, the universe was much smaller at the time. So objects would appear very bright because they were very close to us when that light started on its journey. It took so long to get here because of the expansion of the universe. Space between objects grows, stretching light to longer wavelengths. The expansion of the universe into whatever. The problem is we don't know how much it's expanding outward. They guess about 3 times the speed of light. But they don't know for sure, because in order to know for sure, you have to know what you're expanding into, and we don't know what we're expanding into. So light at the edge of the known universe was emitted 13.8 billion years ago. When that light, the size of the universe was only about 2% of its current size. The universe, therefore, has got to be much larger than 13.8 billion light years because of this expansion. Objects are much, much more distant than 13.8 billion light years. I've had friends of mine that to this day still argue the point that it cannot be more than 13.8 billion light years. People that believe that believe there is no expansion to the universe, except we've known since 1929 or so that the universe does expand. So when that light is coming this way, the universe is getting bigger. It's going that way. So it just stands to reason. Y'all may not be familiar with Brian Cox, but he lectures regularly on the BBC. He is a British musician. He is highly sought after all over the world for the lectures that he gives, because he gives lectures in a very plain, easygoing manner that is easy to follow. This slide is off of one of his lectures. He says, within this diameter lies everything we know. The edge of the universe is 46.5 billion light years away. That is certainly not 13.8. It's much, much bigger. And the reason that is the edge is because light beyond that hasn't had time to get here. So we will never be able to see beyond 46.5 billion light years in any direction because of that fact. So again, and this is called co-moving distance. Co-moving distance is equivalent to proper distance. A lot of times you'll see proper distance stated as a distance factor for it. And it's pretty much taken over astronomy. There's some people, they'll still to this day say, no, nothing can be further than 13.8 billion light years away. And I just nod at them and smile and go on about my business, because they're like the flat earthers. You know, the universe does expand. But anyway, this is, along with the expansion of the universe, is a lot of work that Hubble Space Telescope and the James Webb Telescope has done. And I'm going to show you guys some really interesting pictures, some really interesting facts. This is one of them. In the little small square is the Webb Advanced Deep Extragalactic Survey Galaxy, JADES GSZ14Z. It's the most distant galaxy that we know of that they have discovered. That is as of May of 2025, May of this year. Its distance is 33.9 billion light years away. The light we see was emitted 13.53 billion years ago. That's his redshift. That's his light travel time. That light was emitted 280 million years after the Big Bang event. The universe was at 2% of its present size at the time. So it was much closer when that quasar, or when that galaxy sprang into being. Its proper distance at the time was only 2.67 billion light years. So during that expansion time, 13.53 billion years, the universe has grown to the size where that object went from 2.67 billion light years close to us to a distance of 33.9 billion light years. So that's kind of the way this co-moving radial velocity stuff works. The image on the bottom is the most distant object the Hubble Space Telescope has imaged, and that was in 2015, and it's ZNZ11. It's 32 billion light years away, and it's an interesting object because it has the most distant supermassive black hole that we know of. And not only is it the most distant, but it's 1.6 million solar masses of a black hole. That's 1.6 million times the mass of our sun in an object that came to life only 400 million years after the universe was formed. Astronomers are saying, how can that possibly be? You know, it just doesn't make sense. But a lot of the things that they're finding out in the outer universe really don't make sense. And two things you'll notice about these two galaxies here. Number one, they don't look like spiral galaxies. They don't look anything like galaxies that we're familiar with. That's because they haven't had time to form into anything like galaxies that we know of. Secondly, they're red. They're red because they're highly redshifted. If we could see them up close, they're full of hot, young, blue stars, less than 20 million years old. And some of those stars have solar masses of 150 solar masses. They're type 3 stars that no longer exist today. They were massive, massive stars. And these objects are probably so bright because a lot of them are going supernova. A star of that size would have a lifetime of only a few million years, and then it's going to explode. But that's another thing that they don't understand. How can these distant objects be so bright? They should not be that bright, but yet they are. And there's a group of objects I'll show you later. They're so bright that astronomers are reluctant to even call them galaxies. They don't know what they are. But so far they found 300 of them. So as far as quasars go, how do we know a quasar is really as far out there? Well, we can take the redshift Doppler shift method. We can do a lot of measurements, but a common theme is to look at a Lyman alpha forest, the spectrographic images of these objects. The one on top, 3C273. Is a nearby quasar. It's only 2 billion light years away. It's behind the Virgo galaxy cluster. And you can see there's very few absorption lines. The most of the absorption lines are the Lyman alpha absorption, the tallest one. That's the highest and the most energetic line. The one on the bottom is 22.8 billion light years away, and it's a forest of lines, many, many lines, which is what you would expect. A more distant galaxy, and these are absorption lines, so a more distant galaxy would be absorbed by more dust clouds, gas clouds, galaxies, so on and so forth. So the more distant out you are, the more objects that light has to go through. And you can see that very obviously on this Lyman alpha forest line here. But this is a standard method that you see. Almost every quasar has this kind of spectrographic setup. All right, this is a quasar that I had the Texas Star Party people look at, and I think honestly only Keith Rivage and myself were the only two people that saw it. Or no, wait a minute, I'm getting ahead of myself. This in the year 2000 was the most luminous object that we knew of. It's APM 8279 plus 5255 A, B, and C. It's A, B, and C because it's three components. It's one quasar in the back, but it's lensed by a galaxy in front, and there's three images of that one quasar. And in the present epoch, its age after the Big Bang, it came into existence 1.5 billion years after the Big Bang. It's been traveling, the light of it has been traveling this way for a little over 12 billion years. That means its proper distance today is 23.527 billion light years away. And this is halfway to the edge of the universe. And I guess I misspoke a minute ago. Keith and I did see this one. This was one we had at the Texas Star Party. And if you're into visual astronomy, like I am, and many of the people I know in this room are, that's exciting. I mean, you look at this thing and it's a little speck of light that you can barely see. But when you realize what you're looking at, that little speck of light is halfway to the edge of the universe. That's pretty amazing to be able to see with your own two eyes something halfway to the edge of the universe. You'd expect to have a huge aperture telescope to be able to see that. In actuality, the Hubble Space Telescope can only see out to 32 billion light years. So this is an exceedingly bright object to be able to see something at that far away. 3C273, this is a quasar that I had the Stellafane people look at, and a lot of them came up to me and says, "Oh, we can't see a quasar. You gotta be kidding," And I was kind of chastising them in my talk, and a guy in the front row raised his hand and says, "I've seen it in my 4-inch refractor," which kind of shut up a lot of the people in the room. But it has a V magnitude of 12.9. It's the brightest quasar in the night sky. Its absolute brightness is minus 26.7. That is humongous. What that means is if it was really 10 light years away, 10 million light years away, it's at the same distance as the star Pollux, for instance. If it was at that distance, we would never see the night sky because it would be as bright as the sun. That's how energetic that quasar is. If it was where Pollux is today, it would be a constant daylight, sunlight, bright as our sun. So this is not a particularly energetic quasar. This is just how magnificently energized these objects are. And basically what they are, they're the explosive core of a galaxy, and that galaxy is turned in our direction, so we're able to see the explosive output, the relativistic jet shooting out of the center of that galaxy. And if it's sort of pointed in the direction where we can see it, we call that a quasar. If it's pointed directly at us, we call it a blazar, which I'll show you in just a second. But this is a easy object to see, just 13th magnitude object. People can see it in just about any telescope. Okay, NGC 4319 and Markarian 205. This is an interesting, very interesting object. Markarian 205 is the little fuzzy star-like thing just south of NGC 4319. And 4319 is 77 million light years away. Markarian 205 is 1 billion light years away. But if you look at the bottom picture, there's a light bridge between the two of them. We had in 1995, and then again in 2005, we had Halton Arp as a speaker at the Texas Star Party. And Halton, or Chip as he liked to be called, Chip and I became friends. He spent a lot of time looking through my 36-inch telescope. And I had him up there one night, and I put NGC 4319 on it. And on the side of the galaxy where the quasar was, there was a little brightening there. You couldn't see a bridge, but there's a little brightening there. And I got him up on the ladder, and he looked, and he looked, and he looked, and he finally says, I see it. I actually see it. And he looked at me and says, Larry, I ran the 200-inch telescope for 20 years at Mount Palomar, and I never saw that. Needless to say, that made my star party. But Chip was a very, very nice man. He relished in his notoriety. He did not believe the redshift had anything to do with distance. His idea was the redshift was newly formed matter that was thrown out of galaxies, that was created out of galaxies. And that's why everything was red-shifted. In his book, there was nothing blue-shifted. It was always red-shifted, and it was new matter. And he told me once he never expected to live to see his theories proven, but he figured some of them someday would be. As it turns out, probably none of them would be. But I don't think Chip would care. He relished his notoriety. The last time I saw him, I drove him to the airport, and he was walking down the ramp. I told him, I said, Chip, can we get you back in another 10 years? And he looked at me and says, how about 5? At the Texas Star Party, he got respect, and he didn't necessarily get that at other places. His first visit there, when he was, as a 75-year-old man, he showed up with his tennis rackets, and he was playing tennis on the tennis court. He and I kept in touch when he moved back to Germany. And all of a sudden, I sent him an email and I didn't get an answer. A few weeks later, he had died. He had passed away, But he's another towering giant of astronomy, kind of like Al Nagler, but a supremely nice person. Very, very nice person. And I'm very glad I got to meet and spend time with Chip. NGC 4319 is an interesting galaxy in itself because it's a Seyfert galaxy. It's an active galaxy. It has an active nucleus that's throwing out material at a very, very high rate of speed. This is an interesting object, BL Lacerda. It is classified as a quasar. SIMBAD calls it an active galactic nuclei. They don't consider it a Seyfert galaxy. Seyfert galaxies were named after Carl Seyfert, who back in the 1940s did a group of galaxies that had active cores, active centers. So we call these objects Seyfert galaxies. This is as active as a Seyfert, but it's given the AGN classification, active galactic nuclei. It is called BL Lacerda because originally they thought it was a variable star. It was cataloged as a variable star. But it's different. We're seeing the relativistic jet of it, and what makes it a blazar is that jet is pointed directly at us. We're looking right down the throat of it. And the difference between a blazar And a quasar has a continuous spectrum all across the spectrum. Blazar has no spectrum. It's a featureless spectrum because everything is blotted out because that light is coming directly at us. They call it a relativistic jet because it's traveling practically almost at the speed of light. And in the middle is a supermassive black hole, and it's easily seen in small telescopes, and it has a distance of 900 million light years. So you're seeing an object really far out, but you're also seeing a very bright object, and it's bright because of that jet pointing right at us. All right, a little bit about galaxies. And these are galaxies that I had the folks at Stellafane look at. And I'm going to talk about some of them here, but most of them not. Some other things I'm going to cover. This next slide is interesting. That looks like a lady with a bad hairdo that's screaming at us. But it's a fairly new discovery. It's called a tidal disruption event. And what you're looking at is a black hole that's actually eating a star. A star is falling into that black hole, and they've only seen about 100 of these events. These black holes come in different sizes. When we say it's a supermassive black hole, that's a black hole of in excess of 1 million solar masses. If it's an intermediate black hole, and it took astronomers a long time to find intermediate black holes, but those are 100 to 1 million solar mass black holes. And stellar black holes are anywhere from 1 to 100 solar mass black holes. So these black holes come in all sizes, but when stars, they don't really get sucked into it. The common phrase is that black holes don't suck, and they don't. But if a star happens to run into it and gets caught within the accretion disk, within the magnetic field, then it gets strung out like a piece of spaghetti. They call that spaghettification. And that's what it's showing here. That's a star that's being wrapped around the black hole and being actually sucked in to the black hole. But as it goes in, half the material goes in, half the material goes out. About only 1% of that is relativistic, that is spewing out at the speed of light. The part that goes out is called Hawking radiation, named after Stephen Hawking. And there's only about 100 of these objects that they have discovered so far. But in addition to this, that's even more obscure, is that they're finding that some of these events have what they call a cosmic burp, or a cosmic indigestion. Anywhere from up to 1,000 days or so, all of a sudden, it has another eruption. After it's eaten this star, it goes quiet, and then all of a sudden, poof, something else happens. They don't know why that is, but there's two theories. One is that maybe it continued, but a dust cloud got in the way and kept us from seeing it. But a more better theory is that relativistic jet that's shooting out, when it first leaves the quasar, it's parabolic in nature. It's parallel rays. But after a ways, it ends up a conical type feature. It spreads out. So if it's not pointing at Earth, if it's pointing in this direction, we may not see the parabolic part, but when the conical part opens up, that's what we see after up to 1,000 days or so. But they really don't know why these objects have this seemingly supernova type explosion. They go quiet, and then they have another supernova type explosion. So that's just another one of the mysteries that I'm sharing with you guys. Some other recent discoveries. I told you about the objects near the edge of the universe that we're finding puzzling, if not difficult. some of the galaxy recently discoveries, they found that about 50% of all galaxies are actually members of galaxy clusters and are not galaxies by themselves. And which to me is surprising, which I found in writing these books. Many, many spiral galaxies, you'd think all the revolving is all in one direction. And that is really not true. A lot of spirals may have the stars in the gas going counterclockwise, but the hydrogen emission is going this way, in opposite direction. Or in this particular galaxy here, NGC 613, you've got a galaxy that is rotating in a counterclockwise fashion, but the neutral hydrogen is rotating perpendicular to that rotation. The only way this can happen is if there's some type of an interaction with another object, a dwarf galaxy, or something has happened to throw the rotation curves out of balance. But that happens quite frequently in spiral galaxies, where you'd think they're all rotating in the same manner, but in some cases, half the galaxy is rotating counterclockwise to the original rotation. Elliptical galaxies, they're finding out the flattening of elliptical galaxies is not due to rapid rotation, but it's due to the movement through space, and that is causing the round spherical ellipticals to be flattened. Call that anisotropy is the terminology for it, but it has nothing to do with rotation, which astronomers used to think. And also, somewhat surprising, they're finding that about 2% of all dwarf galaxies, which are the smallest galaxies we have, actually have black holes in the middle. That is very surprising until you stop and think that some globular clusters, M15 in particular, have a black hole in the center of the globular cluster. So if a globular cluster can have it, why can't a black hole have it? But nevertheless, they recently did a study of 115,000 dwarf galaxies and found that 2% of those actually had a black hole in the center of the dwarf. As far as the early universe go, the James Webb Telescope is setting astronomy afire. The discoveries they're making almost daily, or like when the Hubble Space Telescope first came out, everything they point at is a new discovery. Towards the edge of the universe, they have found 300 of these, they call them mysterious objects. They don't know what to call them. Astronomers are reluctant to say they're galaxies because they're made up of uneven material. They're very, very bright. Normally very bright galaxies are large galaxies. These galaxies are 1,000 light years across, if that. They're very, very small objects, yet they're extremely bright. And even if they try to figure in the 130 mass stars into it, or the supernova goes off, they still can't come up with a math that makes these things right as far as how bright they are. So they don't know what to call them. There probably are galaxies, and astronomers say they probably are galaxies, but they're reluctant to say that. At this point, they don't know what they are. We have up here something called the Great, I can't see it, the Great Galaxy Cluster is about 15 galaxies that are merging. Down below that is 5 galaxies. That's an actual photograph of 5 galaxies that are in the act of merging. And again, these are only a few 100 million years after the birth of the universe. So how is all of this activity taking place? The James Webb Telescope is like most astronomical telescopes, and why most of us are interested in astronomy. It will solve maybe one problem, but it comes up with 10 questions or 20 questions for everything that we understand. And that's what makes the hobby that we're into, the science that we're into, interesting, because you can follow this. You know, like I said in the beginning, you can follow it daily if you want to, which I pretty much do. Have you ever seen a picture of a galaxy that looked like that? That's M74, called the Phantom Galaxy, and it's taken with the James Webb Telescope. is called the Grand Design Galaxy because it has beautiful spiral structure. It's only 32 million light years away. In the center is a lack of gas, so we can see all the way into the center of the galaxy. Essentially, you can almost figure you can see the black hole, and you can see the superstar cluster that's surrounding it. You can see the dust clouds. If you look closely, you can see the little pink dots. Those are star-forming H2 regions that are forming in that galaxy. You see the big round circular feature. I believe that looks like a supernova explosion that cleared out parts of the galaxy. You can see background stars through it. You can never see that with the Hubble Space Telescope or any other telescope that we have for that matter. So this is detail on top of detail that is just absolutely fascinating. Can anybody tell me what this is? Does anybody want to guess what this is? Sombrero? Yeah, good guess. There you go. There's a Hubble Space Telescope image up top. There's a James Webb Telescope image down below. That's unbelievable. In the center, you can see the core of that galaxy very, very well. And you can see that because matter is being gravitationally dumped into the middle, causing it to glow. They say black holes don't glow, but they're the brightest thing in the universe because of this, because of what black holes do. The event horizon and all that goes with it. Additionally, if you look at the disk around it, you see all those little, looks like oatmeal. Those are dust cloud accumulations, and within those dust clouds, stars are forming. This is a lenticular galaxy. Lenticular galaxies are not supposed to be forming stars, but the James Webb Telescope has taught us that this one is, and you can see it in that image. It's happening. Messier 104, it's only 28 million light years away, which is why we can see the detail that we can see. Diameter 50,000 light years. It has 2,000 globular clusters. In the Hubble Space Telescope image, most of those, a good portion of that fuzzy area is globular clusters around this object. But the James Webb image, I mean, that's just tremendous to be able to see that kind of detail in another galaxy. Here's another one, NGC 7496. The Webb infrared camera, you can see with great detail the star-forming regions, the little H2 knots inside. You can see the Hubble Space Telescope where you see the dust clouds on the outside, but you don't see nearly as much star formation as you do with the James Webb. But the thing is, NASA has really done a wonderful job here because these complement one another. The Hubble Space Telescope enables us to look at the ultraviolet in the visible universe in detail we've never been able to see before. The James Webb Telescope takes us a step further and lets us look at the infrared universe. So ultraviolet, visual, infrared, this is basically what we see. We can't see the gamma ray, we can't see the X-ray universe, but this stuff we can. So these two wonderful instruments, they complement each other, and it's exciting again to be able to see galaxies, the universe, in this kind of detail. This is a Seyfert 2 type galaxy. It's a very active galaxy, has a diameter of 75,000 light years. It's in the southern constellation of Grus, and it's a little bit low on our horizon, but it's a very bright galaxy and it's easily seen in amateur instruments. All right, for nebula, emission nebula, reflection nebula, dark nebula. Once again, James Webb is leading the way on this. Sagittarius B2 is the most active star-forming region in our Milky Way galaxy. It's right close to the black hole in the center. It's probably feeding the black hole in the center of our galaxy. Although our black hole only feeds about once every million years, which is fortunate for us because it could be detrimental to life on Earth when it did. But this is a huge star cloud that they really did not know existed in that size. On the upper left is PLCK G287b plus 329. This is the largest known energized cloud that we know of in the universe that James Webb discovered. It's 5 billion light years in diameter, yet it's energized. It is ionized, and again, 5 billion light years in size. How in the world is that possible? It surrounds an entire galaxy cluster. They don't think it's energized by stars. They think it's energized by turbulence and chaotic movement between the galaxies, but they really don't know. They really don't know. This is just another one of the puzzles that the James Webb Telescope has come up with. The Veil Nebula, which all of us have seen and are very familiar with, it is a result of a supernova anywhere from 5 to 10,000 years ago. The star that blew up was about 20 solar masses. It's never been found, and it probably no longer exists. It probably, when it blew up, it disappeared. The diameter of the veil is 130 light years. And if you want to get a good feel of that, if you hold your knuckles out, the third knuckle over is the size of the Veil Nebula in the night sky. So it's a big object, and it takes a low-power telescope in order to see all of it. But it's easily seen with an oxygen 303 filter. It's expanding about 932 miles per hour. And the interesting aspect of this is that they now think it's the product of 2 supernova eruptions, not just one. If you look at NGC 6992 on the left, that is totally different from the rest of the nebula. It's a totally different environment. It has enhanced radio emission. It has a higher magnetic field. It has a strong X-ray infrared emission field. Elevated hydrogen alpha and oxygen 3 emission. It doesn't belong there, but yet it is there. So they think that's a product of maybe a secondary eruption that happened within the same field. This has happened before. The Vela supernova in the southern hemisphere, in the Vela constellation, they think also is a supernova, and that later on a second supernova happened within the same complex, within the same emission site. But this is something new about the Veil Nebula, which is kind of interesting. Dark Nebula, E.E. Barnard did a lot of studies on these. William Herschel thought they were holes in the universe, void spaces. And Barnard initially jumped on that until he was out one summer night and he looked down south and he saw clouds, and those clouds were black and they were blocking stuff out in the background. And he figured out, it's not a hole in the universe, it's a cloud of something that's obscuring the background. He figured that out in 1916 after spending his entire life trying to figure out what these mysterious dark things was. It wasn't until about 1936 when Robert Trumpler found out that those dark things were dust clouds. And that's what was blocking out the black material and why they looked black. And this B86 is a very dark region. It's easily seen. They say if you stood on one side of the nebula and the sun was on the other side, you wouldn't see it. It's so dense. But it's half a light year in diameter. And its dust is not dense. It's about 10 million particles per cubic centimeter, which would be better than any vacuum we can make here on Earth. But yet it's so big, that it blocks out light from the background. Planetary nebula, I'm going to start going a little faster because I think my time's about up. This is M57, the Ring Nebula, and this is a view through the James Webb Telescope. You've never seen an image of M57 that looks like this because you're looking through a lot of dust. They did not know how dusty the Ring Nebula was until they looked at it with the James Webb Telescope. You don't see the blue middle. You barely see the central star. The central star is hot. The James Webb Telescope looks at cold things, long wavelengths of things. So it's not going to show the central star. And what you're seeing when you look at the ring is the torus in the center. And the balloons, the lobes are coming right at us. So we're looking literally through the near lobe, through the torus, the center of the galaxy, and then there's a torus or a lobe on the opposite side. But that lobe is full of dust, and that's what you're seeing here. The ring is only 2,600 light years away. The star in the middle is about 0.6 solar masses, so it's much smaller than our sun. But that dust cloud is amazing, and when they ramp up, boom, that's the outer halo of the ring. And again, that is dust and emission nebula coming out of the center as imaged by James Webb. This is NGC 6537, the spider, red spider nebula. And again, you can see it's all messed up. The central star, they've settled on about 160,000 degrees Kelvin, which is very, very hot. Most planetary nebula central stars are less than 100,000. But there are some estimates that place this up to 500,000 degrees Kelvin. This may be the most energetic planetary that they know of. Yet, with that high energy factor, it has a lot of rich molecular material that are involved. That doesn't make sense. Molecules should not be able to exist in an environment with a star that energized, but yet it's there. The distance to it is 3,000 to 8,000 light years, which is typical for planetary nebula because they really have a difficult time measuring how far planetaries are because they have to look through the dust. They have to look through the gas. They're not stars. They're carbon, oxygen, dwarf stars. They pulsate. They don't act like regular stars, so we can't get a good grasp of how far away they are. Globular clusters. I made a list of the classification, the Shapley-Sawyer globular cluster classification scheme, whereas globular cluster 1 are very compact, and globular clusters 12 are very loosely structured. The problem with this, if you look at it, it really doesn't make sense. You got, on the left, you got 1, 2, 3, 4, 5, and so on and so forth, but they don't really line up with what's more dense and what's loose. And it's the same problem with the galaxy tuning fork that Hubble and them came up with. The reason is that these are all visual observations that they were made, but when you photograph these objects, they don't look like the visual object. So that's a problem with the classification scheme, but nevertheless, this is how they're classified to this day. A cluster with a classification of 4 as a denser core than a cluster with a classification of 7. A classification of 12, which you can see on the lower right, is very loosely structured. Shapley was in charge of Harvard University for many years. He did a lot of work with galaxies, did a lot of work with Cepheid variables. Helen Sawyer, she was instrumental in working with globular clusters. She was the first lady that they let use a telescope, a professional grade telescope, and she images something like 3,000 globular clusters in her lifetime. She was a reigning expert on globular clusters. NGC 6822 is Bernard's Galaxy, and it's full of globulars. These are some globulars that I had people look at the Texas Star Party. Some of them are nice, some of them are not so nice, but it's nice to see something like that in another galaxy. Some of the H2 regions are easily seen. Amelia Goldberg showed me some in her 15-inch telescope a couple of years back. And also, I believe, one of the globular clusters. Right, Amelia? Yeah. So these are objects in another galaxy, but they're visible and certainly viewable in small aperture telescopes. And this galaxy is only 1,500 million light years away, so it's not that far distance. Open clusters. These are some that I had at Stellafane. I want to mention Westerland 1. This is another James Webb image. This is a young superstar cluster, and they found it's the most massive star cluster in our Milky Way galaxy out of all of them. There's a couple of, they call these objects superstar clusters. There's a couple of others called Arches cluster. There's a quintuplet cluster, but those are close to the black hole, close to the center of the galaxy, and they are actively feeding our Milky Way galaxy. Westerland 1 is nowhere near the center of our galaxy, but they have found 24 Wolf-Rayet stars, 50 X-ray sources within this one object. Up to 150 supernovae have gone off in this galaxy. I mean, this is a massive, massive group of stars that we just did not, we knew it was big, but we did not know it was this big, this massive, and this dense. In the end, it will probably end up a globular cluster. It's that big. So a few things about the books, which somebody put up there. These are the books that I've written. I'm currently working on book number 4. These are loosely spring, summer, and fall, each one. And I just made a couple of pictures, some of the pages. The idea is to get people not just to look at an object, but look at something within that object. If you look at M22, why don't you look at a planetary nebula that's inside M22? There should not be planetary nebula in any globular cluster because all those globular clusters, stars, are over 10 billion years old. And planetary nebula shouldn't be in stars that old. They're the product of stars up to 1 to 8 solar masses. All of those stars are gone, have been long gone. But yet there's 4 globular clusters that have planetaries, and I've got finder charts for all 4 of them. So this shows you how to find the planetary nebula in M22. And in like manner, in the Trifid Nebula, there's a star-forming region called TC22. And the idea is on the left, you start off with the constellation, and then you start hop over to the object, and then you have a picture of the object. Or in this case, you have a close-up image where you can find the object. So I'm trying to get people to not depend on their computers, to get out under the sky where you're actually looking up and you know that the object is in a constellation. If you use your computer, you just know it's up there somewhere. But if you star hop and you find it, you know precisely where in the sky it is. You learn the sky, you learn the constellations, and if you do it 2 or 3 times, you can throw that finder chart away. You can find it on anybody's telescope. You don't have to have a computer to find these things. And it makes it much more fun. It makes it much more fun for me, and so that's what I've got in the books. So I'll leave you with a few things to think about. Number 1, astronomy is a humbling and character-building experience. It certainly is, particularly if you're an astrophotographer. I mean, you guys, I don't have the patience for it, but I appreciate all the work that y'all do and that I get from you. This is one I love. Astronomy is much more fun when you are not an astronomer. That's Sir Brian May, who is the lead guitar player for the rock group Queen. and an interesting character, and I would love to get him at the Texas Star Party. He would fit right in. Neil deGrasse Tyson, the universe is under no obligation to make sense to you. That's pretty much true. The more things we find out with the James Webb Telescope, the more that gets true. And then last but not least, a cure for many of the world's problems is simply one gentle dose of starlight to be taken each night before retiring. Leslie Peltier. Boy, that could not be more true than today. I wish everybody in Washington would heed that and go out and look at the night sky. Maybe they could get along with each other. But with that, I want to thank you very much. I hope this has given you some idea of where we're going with professional astronomy, with amateur astronomy, and what a wonderful, beautiful, fantastic universe we all live in and are privileged to look at. Thank you. We have time for questions?
We got the building till 10. We shouldn't take that long.
Rarely I have time for questions. Anybody? Yes.
Larry, you were talking about the structures that were perpendicular, and then we were talking about some rotated clockwise, some rotated the other way.
Right.
In that particular galaxy, does that line up with the bar in that galaxy or no connection?
No, it's probably more lined up with the core. Because you got a galaxy rotating this way, and usually these are gas clouds. So you got stars, nebula, and gas and dust clouds going this way, but you got a hydrogen emission cloud going this way. So you got this rotation and you got that rotation. So they're 90 degrees off, which just seems weird. I mean, just weird. But when you consider, even galaxies on a plane, part of it is rotating this way and part of it is rotating that way, which that just doesn't make sense. But in doing research for these books, that happens fairly common. That's just not unusual to see rotation and counter rotation within the same spiral galaxy. So it happens. Yeah.
Potentially the result of merging?
Do what now?
Potentially the result of merging?
It could be. Well, they think that is what causes it. I mean, something throws the geometry of it out of kilter. Something had to have happened.
One rotating this way?
Yeah. And it also happens with black holes, which I haven't talked about. But when galaxies merge and the black holes merge, if they're rotating together, they tend to rotate into each other. If one is rotating counterclockwise and the other black hole is rotating clockwise, they actually repel. And they can see that with galaxies. They have two centers. The Andromeda, M31, has two black holes in the center. Probably counter-rotating black holes that withdrew. But yeah, it probably has something to do with the interactions. Galaxies are like everything. They're like grains of sand. Everything has a gravitational attraction that's going to pull things to it. So that's the prevalent theory as to what causes that. Oh, I need to get back here.
Yeah.
Okay.
I think the Zoom folks can hear you.
Hello.
And then maybe also repeat the question since they don't have time.
Oh, okay. The question was, how can you have a galaxy that's rotating this way and another cloud that's rotating this way, and it's within the same galaxy? Or how can a galaxy be rotating, if you're looking down, clockwise, but part of it is rotating counterclockwise? And the answer to that is they don't really know. But the main theory is that it probably had this interaction with another galaxy, maybe a dwarf galaxy. Something happened to throw things out of kilter. Yes?
Your books are geared to what size optics?
Anywhere from 15-inch to 36. What I've tried to do is get people to look at things like Minkowski 174, and you say, I can't see that in a 15-inch telescope. Yeah, you can, if you just look. because a lot of these things with weird sounding names you can see in smaller aperture telescopes. I've tried to gear these books with objects that people may think they can't see, but if they get out and try, they actually can see these objects. I can't tell you how many people have come up to me at the Texas Star Party thanking me profusely for getting them to look at Minkowski 174, and they got a 12-inch telescope. They thought in the past, I can't see that, but you put a list out and they try it, and they were able to see it. And they're just gushing. Oh my God. It's like the whole observational astronomy is opened up for them. So I've tried to gear some of those books, some of the objects probably you need a 20-inch, but most of them, I'd say 85 or 90%, you can see them in less than a 20-inch telescope, 15-inch telescope. The Houston Club has a guy named Matt Delavorius who has an 8-inch telescope. He's observed every one of my 24 advanced observing list with his 8-inch telescope. On some of those lists, he's observed every object, all 40 objects that I list. And sometimes I'll be up talking to the group and I'll say something like, well, people with a 15-inch telescope probably shouldn't try this. You know, this is, Argus E147 because you can't see it in less than a 15-inch telescope. It's the same as going up to Matt and slapping him in the face. Because that night, he will have me down at his telescope to see that object. I'll sit there with a black cloth over my head, and I've never been down there that I did not see what I had told those people you need a 15-inch telescope to see it. But I do that particularly for Matt, because he's one of the best observers in the world, and he does it with an 8-inch telescope. So it's hard to say what's the minimum aperture, because people have different eyes, different optics, different skies, but you don't need a 36-inch, 30-inch, or 24-inch telescope to see the stuff in that book. Okay? All right, thank you again.